Hello, I'm Dr. Pippa Petts. Welcome to my presentation on evaluating student understanding of uncertainties. This is the overview of the presentation that I'm going to give today. I'll talk you through what the investigation was, a little bit of the pedagogy background, the methodology that we used, including the 3 particular probes, and then talk a little bit about our statistical analysis and our results. The investigation took place during the 2019-20 academic year, and we investigated the students' comprehension of measurement uncertainties. The students involved were first-year physics undergraduates at Durham University taking the module Discovery Skills, and a small number of natural scientists who were in their second year. Participation in this was entirely voluntary and had no bearing on the course grade at all. We collected data both pre- and post-instruction with online surveys that were specifically designed to probe their understanding of uncertainties. Now a little bit about the pedagogy background to this project. You may well be aware of the idea of threshold concepts. The idea has been around for nearly 20 years now, proposed by Land and Mayer. They state that there are 5 key criteria that define a threshold concept, so they must be transformative, integrative, irreversible, boundary defining and troublesome. And various potential threshold concepts have been proposed in physics, one of which is the measurement of uncertainties in the laboratory. Another relevant piece of pedagogy in particular to this project is the idea of the point and set paradigms, proposed by Lubin et al. So the point paradigm is characterised by the underlying notion that each measurement in principle could be the one true value, and therefore, as a consequence of this, the measurements of other values are not relevant or not combined in any way. This contrasts completely with the set paradigm, which is the notion that each measurement is an approximation of the true value, and the deviation of this is random. And therefore you need to form a distribution by measuring lots of different measurements. This slide shows the progression of skill level and uncertainty, and it's adapted from a paper by Ali et al. So we can see as we move through this wheel from A to H, we move from red to orange to yellow to green. So at the very beginning of this wheel, under section A, the student might say that it's okay to measure a value just once and then you get the correct value doing that. Then they might progress in their ideas and understand that actually you need to view trial attempts before you do it, and then eventually moving on to understanding that you need to take several measurements and calculate the mean. This would be under the emerging skills section. Then they might realise that you need to take a mean of several measurements and that the spread of this is actually an indication of the quality of your data set. And finally, at the top, under the proficient category, they might realise that the consistency of a set of measurements can be judged and that you can reject any anomalies that you find. So we would hope that wherever our students come in on this wheel, that we would be able to get them to the green zone by the end of the module. So because some of our students are the very best in the country and they've attained the highest grades in order to study with us, we would hope that they would come in somewhere in the orange zone. However, experimental lab practice between schools varies greatly, and they might not have ever actually managed to do any practical measurements before. So it's vital that wherever they come in on this wheel, we're able to move them on towards the green area. So this particular survey involved this fictional question of a ball rolling down an incline and landing at some point measured at D away from the table. So we designed a digital questionnaire to test this. There were 8 probes, including one that was graphical. The students answered the questions pre-instruction, then they received a lecture course on error analysis, and then they sat the questionnaire again afterwards. And then we coded the data depending on their particular answers. So of the 7 numerical questions we asked, the repeated measurement probe, RD, the repeated distance probe, is actually one of the most interesting. It's one of the most basic, but it spans quite a wide range of potential answers and complexity. So the question was this. We had a group of students measure the distance D to be 436 millimetres, and then there were 3 student statements, and the students were asked to identify which one they agreed with the most. So the 3 statements were: roll the ball a few more times from the same height and measure D each time. Student B said, why? We've already got a result, we don't need to roll it again. And student C said, I think we should just roll the ball down the slope one more time from the same height. So the students were asked to identify which student they agreed with and then give a written explanation of their reasoning for this. The second two probes were numerical in nature and looked at means and spreads and uncertainties. So the first one, the DMSS, different mean, same spread. Students were given the data in the table shown here, 5 particular measurements, each for Group A and Group B, and their associated means. So here the means are different, the numerical means, but the spread of the data is the same. And the students were asked whether these two data sets agree and to explain their answer. And the final probe I'm going to talk about today is the DMSU, the different mean, same uncertainty. So here we've got two values with a mean with an uncertainty attached. The mean values are different, but the uncertainty, the plus or minus value, is the same. So again, the students were given these values and asked whether these two measurements agree. So the most sophisticated student responses would indicate that both the mean and the standard error need to be involved in this. This figure here shows where our different measurements lie on our complexity scale. So our repeated distance measurement, or RD, at our most basic level, where you say, actually, I just need to take one measurement, we'd be right down in the red zone. Moving up through, I need to take a mean, and then right into the green, talking about standard errors and overlap. Our two numerical probes already start at a higher value because we're already thinking about using a mean, and there are 3 levels of this, ranging from going to the yellow into the green. So the student responses to the 7 questions were scored, and they got a 1 if they passed a level of sophistication and a 0 if they didn't. Our survey was mixed, so we had some paired data for students that did both the pre and post test, and then some unpaired data for students that only did one or other. We used an optimal pooled t-test, with the statistics shown there. A low sophistication would be something like the means are close or far apart, and a high level would be talking about the standard error. So something like the means don't lie within 3 standard errors, and an excellent agreement would be if the means lie within 1 standard error. This test provides a weighting that is inversely proportional to the variance of the estimates. We then compared the t-test statistic to a t-distribution table. This table here shows the learning gain in the particular probes. So we can see that particularly for the probe looking at the repeated measurement, we don't show an increase in learning gain even at the 10% level. But overall we see scores increasing at a significance level of less than 0.1%. So the agreement level probes were much more sophisticated in the pre-test measurements. The answers shifted away from numerical values and towards more sophisticated measurements like standard deviation and standard error. However, the caveat to this is there were still around half the students that gave some of the most basic answers, particularly in the repeated distance test, which is concerning. This figure here shows a comparison of all 7 of the numerical probes that we used. We can see the biggest increase in our post-test measurements is in the DMOS and the DMSS. So this is different mean outside spread and different mean same spread. The repeated distance was chosen for discussion because actually it showed a large potential for students to improve their scores, though some of them still are in this liminal state where they're actually giving quite complex answers in some questions, but in some of the more simple ones they're reverting back to their much more simplistic numerical comparisons. So these are the raw numbers for our particular tests. So in table 3 we've got our repeated distance, our RD probe. We can see that the percentage change where we go from R1 to 2 to 3 to 4 to 7. Our numbers go down and we get a much greater increase in our RD7, our highest level of sophistication. No students actually mentioned this in the pre-test at all, but we had 33% mentioning it in the post-test, which is great. Table 4 shows the data for our 2 numerical values, so our DMSS and our DMSU. So the good news here is that both our basic level, our DM1, our lowest level of comprehension, go down by a whopping 45% in the DMSS, and our 2 higher levels go up. So our DM3s are increasing, which is great. So what we've seen in this study that there was a statistically significant improvement in the performance of the students between the pre- and post-test surveys. So we can conclude from that the module is somewhat successful in transitioning students from the point to set paradigms that are associated with this threshold concept. However, there are more students than we would like that are still giving either mixed answers or are reverting to some of these much more basic concepts. So this suggests that they're in a liminal state and they haven't quite moved through this boundary. Therefore, we need to work a little bit more on the instruction methods for this module and see if we can change that. We'd like to thank all the undergraduates that participated in this project, and also Sam Nightingale, who was the master's student who designed the probes and did the data analysis for this. I'd be very glad to answer any questions that you have on this presentation.